This is an introductory module to section 4.6 and variation of parameters, where we are going to find a new method to find YP, a particular solution. We'll talk a little bit about where it comes from and then a little bit about the method itself. So basically, first of all, when can we apply this method? Well, we can apply it to second order linear differential equations, such as this one. And here I'm wanting this to be F because the rest of my slides have an F. This is the function that's right next to the equal sign. I'm going to call f of x. And as you can see, this is a linear differential equation. So where does the method come from? Well, suppose that we can somehow solve the homogeneous equation. Setting this to 0, we then somehow find y1 and y2, and we create the homogeneous solution part of the general solution. Well, then there's this idea that y1 and y2 then must solve the differential equation. And so what we do is we take y1 and y2 and we multiply each of them by a function, say u1 and u2. Now we don't know what u1 and u2 are, but we're just thinking that since y1 and y2 solve the differential equation, then maybe y1 times a function, y2 times a function would also solve the differential equation. And in fact, this has turned out to be a very good trick in differential equations. If you're looking for another solution, you sometimes take the solution that you already have times a function and then look for that function to see what it might be. So in this case, we are then, if we could find u1 and u2, we would be done, because y1 and y2 we've already found right here. So through doing a bit of manipulation, making sure that yp satisfies the differential equation, meaning I find yp prime, yp double prime, and then I put it into the original differential equation, then I get to these two differential equations right here. And you can see the derivation in the textbook. So I have two, not differential equations, sorry, two equations. These two equations are in two unknowns. You can see that u1 prime, u2 prime are the functions that we don't know. y1, y2, y1 prime, y2 prime, we know because we already have found y1 and y2. And so we have a system of two equations, two unknowns, and we can solve that. And in fact, we'll use Cramer's rule. That's what this method leads us to, is to use Cramer's rule to solve it. You don't have to be that familiar with Cramer's rule. It is something you would learn in linear algebra. But we're going to use the result from Cramer's rule. So what we do is we find these three determinants, W, W1, and W2. W is basically the wrong skin of y1 and y2. So we take y1, y1 prime, y2, y2 prime, take that determinant, and then W1 is the determinant of the same matrix as we have in W, except that the first, you see that's what that 1 means, the first column is replaced by a 0 in f of x, the function to the right of the equal sign. Then we find that determinant, and then we find W2, which is the same idea. Again, the 2 shows me that on the second column I'm going to replace W. You see the first column is the same as the one in W, but the second column is now 0 f of x. And then I find that determinant. Well, Cramer's rule would basically tell me that u1 prime is equal to w1 over w, and u2 prime is equal to w2 over w. So now what I'm looking for, you see, was yp. And to know yp, I need u1 of x and u2 of x. So to get to u1 of x, I just find the integral of u1 prime dx. And to get to u2, I find the integral of u2 prime dx. Once I find u1 and u2, then I have yp. I already knew yc, so finally the general solution is yc plus yp, as I've already had them. The nice thing about this method is that you no longer, it works for other functions other than the ones in the table in section 4.4. 4.4 gives us a table for just a few functions. But here now we can handle almost anything to the right-hand side of the equal sign.